All right. Hi, everybody. We are now on our first topic in General Physics 2. For the first set of topics in this class, I will be with you. My name is Sir Josh. So, John Wesley once said that electricity is the soul of the universe. And indeed, this is one of the traces of nature that electricity is the one that makes our universe alive. We have electric charges in our bodies. We use electricity in our daily lives. And I think life wouldn't be possible without electric charges and electricity. And electric charges, these are fundamental in our existence in the universe. And therefore, as physicists, as ordinary citizens of the universe, we must be able to know what electricity means, what electric charges mean, and um, what can we know more about them. These are our objectives for this session. Number one, we'll try to define electric charge and describe how the two types of charge interact in subatomic particles. Number two is we will explain the role of electron transfer in electrostatic charging. Number three, we state the law of conservation of charges either by conduction, friction, and induction. I hope they sound exciting. All right. So if you check your Pearson eText, this is under chapter 21, pages 707 to 713. This is General Physics 2, and let us begin. Our discussion about electric charges, I would like to start with going back to the fundamentals, to the microscopic level, and this is navigating and trying to dismantle what is inside an atom. So we have learned in elementary and consistently in junior high school that there are three major components of an atom. It contains protons, electrons, and neutrons. At the very heart of your atom is what you call the nucleus. And inside your nucleus, of course, you have the proton and the neutron. The proton is said to be positively charged. The neutron has no charge, or we say it's neutral, and the electrons around the nucleus are negatively charged. Of course, we know this from junior high school, but I think it's worth the recall and review. Going back further, electrons were discovered by Sir J. Thomson, and Thomson actually proposed a model whereby the negatively charged um, corpuscles were distributed in a uniform sea of positive charge. So this was known as the Plum pudding model. So the Plum pudding model is actually a famous British dessert. Of course, you have a plum and then you have raisins in it. But if you're not so familiar with this, I think we have our local version. We call it the binangkal. No, so where you can see sesame seeds being spread out around that spherical shape of binangkal. But anyway, in the parlance or in the technical term of Sir J. Thomson, he called it as corpuscles, not yet electrons. No, it was only later on that this was called as electrons. So as you can see in his model, basically according to him, if this is the atom, around on it are of course are your electrons. And the matter here is said to be positively charged. They were distributed in a uniform sea of positive charges. Of course, this model has improved and has evolved and has become more comprehensive, and it actually um, led into what we call the electron cloud model. Now, one thing that we should always keep in mind as we study electrons is that electrons are are very fast. They move very fast, and such that it's difficult to determine its exact location. All right. Since it's difficult to locate the exact location of electrons, there is what we call an electron cloud. And this electron cloud is a region. Okay, this is a region of the negative charge that surrounds your atomic nucleus, and this is associated with atomic orbital. So, by definition, we say electron cloud is a region where there is a high probability that your electrons are there. This is the most probabilistic location of your electrons. All right. So in other words, the models that we see from the Bohr's model to Sir Thompson's model, which is the plum pudding model, is an oversimplistic model. A more comprehensive and a more realistic model is the electron cloud model. This is studied by Heisenberg with his uncertainty principle, of course, Schrödinger, as he was studying also um, um, quantum mechanics, and he was also studying the different states, okay, of these electrons. There is what we call the law of charges. This law of charges is much more of describing the behavior of electric charges depending on its interaction with what kind of charge. So it's very simple, and I think we know this. We are familiar with this. It technically says the law of electric charges states that like charges or the same charges repel and opposite charges attract. Let me read that again for you. Like charges repel and opposite charges attract. Meaning to say, if you have a positive charge and a positive charge, since they are they are of the same charge, they will really repel. And if you have a positive and a negative charge, they will attract to each other. So protons are positively charged, electrons are negatively charged, therefore they are attracted to each other. So that is the law of electric charge. No, if we put it at the simplest form of it. And in terms of symbol, we represent positive charge with a plus sign, and then we represent a negative charge with like a minus sign or a subtraction sign, right? Okay. So as you can also see here, there is an illustration there, or a representation of arrows. No, repel meaning they go opposite side. The arrowheads go opposite side, and the attract, they actually try to face each other. So that's how we represent also our interaction between charges. All right. So for instance, you have here objects that have the same charge. They are going to repel each other. Why they repel each other? Because each object exerts a force on other object. So this charge over here in the first illustration, let me get my pointer. All right. So the first, the charge over here, as you can see, is positive, and the other one here is also positive, right? So since both are positive, this charge here will have to exert a force to the other object, and the same thing, this object here also exerts a force. So the forces now push the objects apart. So the direction of force that they actually also apply depends on the charge that they have. Like this one, if the other object, they have opposite charges. So this charge is negative, and then this charge is positive. So they are actually attracting each other because the force that they exert is pulling. These forces pull the objects together. All right? So that is the law of electric charges. So, in summary, how do we define electric charge? This is the property of subatomic particles that causes it to experience a force when placed in an electromagnetic field. So, I want it to be described as more specific as possible. Property, we say that that is an intrinsic property. You know, electric charge is an intrinsic property of matter, meaning to say it's already there. It's there. So it's like, why it's there? It's so difficult to answer that. It's like answering why am I here on Earth? No. So our task, therefore, as physics students here, is to describe electric charge, not necessarily explain the existence of electric charge. So it is like your mass, it is like your time, it is like your distance, it is like your say um voltage. It is something intrinsic. It's an inherited property, no? So it's very it's a natural property, right? So our job here is not to um, um, prescribe things, but we are here to describe, no? So that is the definition of an electric charge. Now, we will be discussing electric force in a different discussion, but since we have already mentioned the word electric force, for now, let us just define electric force and try to know at this point, at the very least, what are the factors that affects your electric force. All right. So number one, we say that electric force is the force between charge object. All right. So if you have a positive charge and you have a negative charge, we say there is an attraction since they have opposite charges. And that attraction, that force is what we call the electric force. All right. So if you have charge object, another charge object, regardless of the charge, when they do have an interaction, there's already electric force in there. So what now determines the amount or the size of electric force? Number one, the amount of charge. Okay, so the greater the charge, the greater the force. It's like when you are playing a tug of war game. No, let's say the tug of war could be the repulsion of things. No, if the other side, if there are more charges in there, it's a big amount of charge, then of course we expect that they will have a greater force, right? And of course, another thing is the distance between charges. So the farther the distance, the less the force. Sorry for the typo. The farther, that's FA. The farther the distance, the less the force. Meaning to say, distance is also a factor. No? So I think that totally makes sense. That's very straightforward. So as of now, remember that what affects electric force is number one, the amount of charge, and number two, the distance between these two charges, or three charges, or four charges. All right. And I think I've also made mention about electric field. So this is the thing that for now you need to know. All right. Number one, electric field is the region around a charged object. Okay, so let's stop in there. So where can you find an electric field? Electric field is a region around a charged object. So if you have a negative charge, automatically it will have an electric field. Okay. Now, what does the electric field um, what does it do? No, this is a location or a region where your electric forces can be exerted on another object. So this is where your electric forces are actually possible. Okay, so meaning to say there are also electric field is something that's limited. because outside the electric field there can be no forces, no, as far as that charges are concerned. So again, electric field is a region around a charged object, either it's positively charged or negatively charged. So when you have a negatively charged object, automatically it will have an electric field, and on that electric field, that is where the electric forces are possibly exerted. All right. So it's like the arena of electric reaction or electric force interaction. All right. Now, why do objects are charged? Why do these objects are getting charged? Okay. So why do you have a positive charge and why do you have a negatively charged object? So um, generally, and you've learned this in general chemistry, that atoms don't have a charge because they have equal number of electrons and protons, or in short, they have equal number of positive charges and you have equal number of negative charges. So for instance, we have here an atom. That atom contains 3 protons and you have 3 electrons. Since you have equal number of electrons and protons, they cancel out each other and you produce a neutral object, or an object that doesn't have any charge. But when these objects gain or lose electrons, they now become charged. So in short, objects get charged because they gain or lose electrons. All right? So why not protons? Why not protons? Because as we know, at the very core of your atom, at the heart of your atom, it's inside the nucleus and it's bonded, or it's bound with um, your neutron because of a binding force, which we'll also discuss in future topics. And your electrons are the only one that get gained or being loose. Okay, so it's only your electrons. So it's the electrons that transfer from one object to another. All right. So for instance, you have 3 protons and then there is 5 electrons. So in this case, the 3 protons and the 3 electrons will cancel out, and you have two remaining, two negative charges. So therefore, your object now is negatively charged because you have an excess of 2 negative charges. How about the second example? You have 7 protons and you have 2 electrons. You have 7 positive charges and you have 2 negative charges. And now, when we add them, only 2 protons and 2 electrons cancel each other out. So there are 5 more positive charges, and we say that that object is a positively charged object. I hope you got that. Now, how do we charge them? How do we make it positively charged? How can we gain and lose electrons? So there are 3 ways. Number 1, by friction. Number 2, by conduction. And number 3, by induction. Just a reminder to all of you that each of these ways to charge an object, it means that only the electrons move. The protons stay in the nucleus. Sana almost stay. All right. Okay. Now, before we fully understand and appreciate the process of electron transfer, or yeah, of electron transfer and charging, we have to review the concept of electron affinity. Okay, so electron affinity, this is something that you learned in chemistry. This is actually one of the periodic table trends. Electron affinity from left to right increases, and then from bottom to top, it also increases. Okay, double check that one. All right, so when we say electron affinity, this is the property of electron, okay, that refers to the relative amount of love that a material has for electrons. So when we say electron affinity, meaning to say it's the material's tendency, to love electrons. So if atoms of a material have high electron affinity, then that material will have a relatively high love for electrons. And that will explain that some materials don't love electrons and some materials do, because they have different levels or different degrees of electron affinities. All right? So, another thing that we need to review and understand by now is the concept of conductors and insulators. We'll be having a separate intensive discussion about this and about circuits in the future. But for now, let us just review and hopefully well at the same level of understanding that electrical conductors are materials through which your charges can move easily. Okay? So these are your metals, these are usually your wires, no, so that you can make the electrons free to move. You also have your copper, your aluminum, your mercury. These are said also to be good conductors. Okay. Then, when you say insulator, insulator is a material in which charges cannot move easily. So when you say insulator, it doesn't mean the electrons really don't move, but it's just that they cannot move that with much freedom because of its molecular and atomic arrangement. No, so in terms of conduction, meaning to say that does it allow electrons to flow freely? No, because electrons here are tightly held in the atoms of insulator. So these are your plastic, your rubber, your glass, the wood, and sometimes air. But at times, air can also be a conductor, but it depends on its composition because remember, air is a mixture. So, but generally speaking, air is an insulator. Okay? So that's very easy to understand. I hope you understand. So if you have any question, ask me, or if I'm your teacher, or you can ask your respective physics teacher. I'm very sure they're more than willing to assist you. All right. Let us start our discussion first by friction. Okay. Now, friction, usually we know this, especially if you're a Boy Scout or you're a Girl Scout. No, you are very well aware of this. No, making fire out of friction. Um, the other term for friction is triboelectric charging. So when you say, I would like to charge my object by friction, I can say it's the triboelectric charging. Okay, so hopefully that's a new learning for you. So friction is also known as triboelectric charging. So maybe sometimes if you want to sound better or if you sound smart, then you should use triboelectric charging. Oh, let's do triboelectric charging. All right. So how do you do friction? How do you do triboelectric charging? By the way, why it's called triboelectric charging? It's called that way because there is what we call the study of friction, and the study of friction is what we call tribology. That's tribology. And of course, since we're transferring electrons, so you have electric, so triboelectric charging. Okay, wala na, share ako. Okay. Charging by friction occurs when electrons are wiped from one object onto another. So this one requires contact of the two objects or more. So for instance, you have a cloth to rub a plastic ruler. The electrons move from the cloth to the ruler, and the ruler gains electrons and the cloth loses electrons. Okay, so that's easier said, but I hope you're able to visualize that. But I have here a presentation that hopefully you can understand. Okay, I will try to um, present that to you. Okay, so hopefully you can see my screen right now. So what you have here is you have like a sweatshirt, and then you have here a balloon. So as you can see, These objects here are all neutrally charged, meaning to say they have equal numbers of protons, or they have equal numbers of positively charged, and they have also equal number of negatively charged particles. Okay, they have negative charges and you have positive charges. They are equal. Now what will happen is, if I will transfer charges by friction, meaning to say I have to put the balloon in contact with the sweatshirt and I have to rub it. RUB. I'm rubbing now it to the sweatshirt. So as you can see, as I rub it, the balloon gains negative charges and the sweatshirt now has lost, okay, negative charges. So in short, your sweatshirt becomes positively charged and your balloon becomes negatively charged. So if I release this, my sweatshirt now and the balloon can be attracted to each other because there is a positive side in the sweatshirt and then you have a negative side here in the balloon. So there is now attraction. And that transfer of charges, no, is what we call charging by friction. So we get the sweatshirt charged, positively charged, because we actually transfer the electrons to the balloons, or the electrons transferred to the balloons. And we got the balloon negatively charged because we rubbed it to the surface of the sweatshirt. So in other words, we now transfer electrons by friction, by tribological process, by rubbing two things together. So that is what we call charging by friction. Okay, so I hope you're able to visualize that more through this illustration. This is also available in your Pearson account. You may just look for balloons and electricity under simulations. Okay, so allow me to continue then. So at the molecular level or at the atomic level, what's happening is the electron clouds of the two types of atoms are pressing each other together. Diba? You have two sets of electron clouds now because you have two sets of objects. So what happens when they are pressed together, so meaning they have to be intensely rubbed against each other, they are brought closer to the nuclei of the other atoms. And the protons in the atoms of one material begin to interact with the electrons present on the other material. And what's happening is you're able now to transfer electrons, no, from one object. So the other one gains and the other one loses. All right. So that's what we call by charging by friction. Let's proceed to the second example of other way of charging an object. Um, we are we can charge an object by means of conduction. This one is, I think, the one of the things that we use every day. No, we conduct things every day. When this is happening when electrons move from one object to another through direct contact without the effort of making friction or rubbing each other. You simply put them in contact, then the electrons directly move from one object to another. So for instance, suppose you touch a charged piece of metal with a positively charged glass rod. Electrons from the metal will move to the glass rod and the metal loses electrons and becomes positively charged. All right, so what does this mean? So for instance, you have here a spherical metal. This spherical metal is being hung. Of course, you have a string there. Now, this is neutral. So meaning to say this may have charges, but the charges in here are equal in terms of the number of positive charges and negative charges. Now, let's say you have here a negatively, okay, a negatively a negatively charged object, the negative charge object here will be conducted since you put it in contact with the metal sphere. So that will be conducted. The electrons will move freely, okay, from this object, from this negatively charged rod to the uncharged metal sphere. So in other words, your sphere now, from being neutral, it becomes charged. All right. So that is how we do charging by conduction. So there is a free transfer. Okay. There's a free transfer of electrons from one object to another by contact. Okay. So that's what we call conduction. Okay. The third type charging is by induction. So what is happening here in the induction? In induction, the transfer of charges, okay, are happening without direct contact. So it says there, charges in an uncharged object are rearranged without direct contact with a charged object. So our keywords here are rearrangement without direct contact. So how is it possible to rearrange our positive and negative charges? All right. Sige. So I think I have here a material for that. All right. Let's start to play this. So let's try to make a metal sphere positively. Okay, nag-una siya. So what is happening here is you have a negatively charged rod, and then you have here a neutral, and you have here neutral sphere. Now, what will happen is that when you place this negatively charged rod so close to the neutrally charged um, metal sphere, what will happen is that these charges in here will rearrange. Okay, they will be rearranging themselves such that the positive charges will have to go to the side nearer to the negatively charged rod, and the negative charges in the metal sphere will have to go away from the negatively charged rod. So therefore, there is a rearrangement of negative charges here and positive charges here. So why is that so? Because the charges now are being induced. It is the process of induction. Okay, so these charges over here are what we call the induced charges, because you have here a negatively charged glass rod. It was able to rearrange this one, and the negative charge goes in here, and the positive charge goes near the rod. Again, they are not in contact, no, because um, the charges here are not able to escape because it is surrounded by insulators. So the stand used here is an insulator, so meaning to say the electrons cannot also go there, and the positively charged objects cannot transfer or cannot be attracted here directly in contact because there is air which acts also as the insulator. So let's see what happens next in here. Now, let us say we will now make a connection to the ground. So what's happening is the negative charges now flows because we make a ground in here, and then say we disconnect the ground. All right. Observe properly what happens to the charges now. They are now again uniformly distributed, okay, in your metal sphere, since you have detached or you have moved farther the negatively charged. So in summation, you have here, all right? So the charges here are being induced, all right? Let me pause at the summary part. All right. Okay. Ah, sorry. Okay. So what is happening here in summary is you are making the metal sphere negatively charged by one, having here a positively charged rod, and then what you're doing is you are inducing, okay, inducing the opposite charge of the rod. So say it's this positive, so the one it will induce here, or attract here, is what you call the negative charges. And of course, the other side here will be placed in here, or the other charges will be placed in here, the positively charged particles. And then you have here, um, if you connect it to the ground, so basically there's nothing else happening here aside from the induction, no, the rearrangement of charges, because everything is insulated. The stand is insulated, air is an insulator here. But when we create a connection to the ground here, we make a ground, what happens is that your charges, okay, your charges now escapes, and you create a charge object. So this is the summary or the process of charging by induction, by bringing a positively charged glass rod um, close to a metal sphere. All right. So hopefully you're able to see the summary of induction. Now, in another example here is if you charge up a balloon through friction and place the balloon near pieces of paper, the charges of the paper will be rearranged and the paper will be attracted to balloon. So the induction part here is the rearrangement of charges. So I'll try to see if we can still make use of this one. So, all right. So this is basically induction, no? Rearrangement of the positive and negative charges. So if I place here the balloon, remember is negatively charged, right? Okay, I will have to have a set of balloon. Have to reset them. Okay. So if I place my balloon, I rub it off. As what you can see in here is there is a rearrangement of your charges. uh. So in our example here, if you have a balloon and then I will charge it up by friction, and I will place the balloon near pieces of paper. So the arrangement of the charges in your paper will be rearranged, and eventually, it will be attracted to the balloon. So that's how you charge objects by induction. In summary, we can describe everything, the movement of the charges, by the law of the conservation of charge. No? So the law says that when you charge something and anything by any method, either induction, conduction, or triboelectric charging, no charges are created or destroyed. All right? No charges are created, no destroyed. What you are doing is you are only transferring. Electrons simply move from one atom to another which makes areas that have different charges. Again, you are not creating any charge, you are not destroying the charges, but what you are doing is you are simply making the atoms move, okay, from one place or from one object to another. Therefore, you are conserving the number of electric charges. So if we are going to demonstrate this one, okay, in here, we will reset this one. Let's say, for example, we have 100 positive charges here, and you have 100 negative. So you have negative 100, 100 negative charges, and you have 100 positive charges. All right. If I will rub this, I will make friction here, and then okay, the objects now are charged, positively charged and negatively charged. The fact still remains that the number of charges is not diminished nor increased in the system. So we can say that electric charge is therefore conserved. And that's the meaning of the law of electric charges. Okay? All right. Then the last topic for this slide is about static electricity. Okay? We define static electricity as electric charge at rest on an object. So basically, this is the kind of electricity that is not moving because it's static. So when you say something is static, meaning it's not moving. So the charges of static electricity do not move away from the object. So they are in the object. So the object keeps its charge. So for example, you have clothes taken out of the dryer. They are actually having some static electricity. That's why sometimes you feel get uh charge also, or you not charge, but you feel get shocked. No, so I'm not sure if you've tried that when you get clothes from the dryer. Mura kag makurentihan usahay. It's not because the dryer is still functioning, but there are actually electric charges in there. There's static electricity. Sana all na ay dryer, sir. All right. Now, when this static electricity is being released, okay, when they move off an object, we call that as an electric discharge. Okay, so when you have charges and then they move off, we call that electric discharge. So sometimes electric discharge happens slowly. For example, the static on clothes, and sometimes, most of the times, we do not notice it, but sometimes they also happen quickly. For example, is wearing rubber soled shoes on a carpet and lightning. Okay, that's an example of an electric discharge. I'll be putting a video in there about the explanation of lightning in the principle of electric discharge and static electricity. So I'm not sure if you've experienced this, but also with a doorknob, there could be an electric discharge in there because there's static electricity. So I have here a simulation. This is called the John Travoltage. So this is John Travoltage. So what you have here is I'll put the finger of John Travoltage in contact with the doorknob and say John is actually on the carpet. So if there is now electrons, okay, in there, or negative charges, okay. All right. So basically, okay. So if you have here negative charges around your body, okay. So you will feel that you get shocked sometimes because of course the doorknob is the doorknob is an conductor of this negatively charged. Okay? So that is a simulation of electric discharge. All right. So I think that will be the last slide for this presentation. So thank you very much, everybody. Below, watch the electric lightning as an example of electric discharge, and I hope you learned something from this lecture of mine. God bless everybody, and don't forget to take down notes.